So hello everybody. So today we have welcome to today's seminar, and today we have Abhijit Gadde from TFR, who will tell us about multipartite entanglement and RG or coarse graining and holography. Okay, over to you, Abhijit.
Okay, thank you very much, Ayan, for inviting me to this seminar series. Let me also apologize that I couldn't make it in the person, make it to the talk in person. So in future, hopefully, when it is less hectic here, I would certainly love to visit Chennai. Okay, so so the title that I sent to Ayan was Monotonicity of Quantum States or something like that, which of course is a valid title, but I decided to make it a bit more catchy. So now the new title is What's Special About Holographic States? Okay, so this is a work that we have been doing over a period of last couple of years with a set of students, Shreyans Jain. So my PhD students are Shreyans Jain, Prakshu Sharma, Vinit Krishna, and also an exceptional undergraduate student, Harshal Kulkarni. And we have 3 papers in the series out already, and we have 1 paper upcoming, which will tell the story that I'm going to tell today. It will be based on the papers that I've already listed here. Okay. So let me first try to explain what I mean by this question when I ask what is special about holographic states. First of all, let me say what I mean by holographic states. So these are states of a conformal field theory that admits holographic dual, gravity dual, more accurately, because you could also have a dual which will have stringy states. So that's not what I'm concerned with. So I will consider CFTs that admit gravity dual. And the conventional wisdom is that if a conformal field theory has a large central charge, which means weak gravity, and a large gap, which means that there are no higher spin massive states that are hanging around at low energies, then this CFT is expected to have a dual that is discrete by Einstein gravity. So these are the kind of CFTs that I will focus and try to make certain statements that are universally true about such CFTs, about the states in such CFTs. Okay, so in today's talk, I will illustrate my points using 2D CFTs, 2D holographic CFTs. But most of what I say, in fact, almost all of what I say will work for higher dimensional CFTs. Okay. So let's start by considering a concrete example of a CFT state, let's say vacuum. But again, the state of the CFT in question could also be different than vacuum state, but this will make us easier to make the points. So let's start a 2D CFT. Let's take a 2D CFT on a circle and consider it in a vacuum state. So as you know, such a state can be prepared by a path integral on a hemisphere, as the picture suggests. Okay. Now what I've done here is I've decorated this picture with additional structure. Namely, I've pointed out 3 regions on the boundary A, B, C, in addition to doing the path integral and constructing the state. Okay, so this is state psi. So in addition to that, I have regions A, B, C marked out on the boundary. Now, quantum field theory is a subtle thing. You cannot quite associate Hilbert spaces to regions. That's why one has to work with these algebras of operators in defining entanglement, entropy, etc. in quantum field theory. But nevertheless, we will take a more traditional viewpoint and associate Hilbert spaces to local regions A and B and C, which we'll call HA, HB, and HC. Okay, so the full Hilbert space of the CFT is a tensor product of the Hilbert spaces attached to regions A, B, and C. And the state that I've created using the path integral lives in this tensor product, okay, which naturally makes this a multipartite state. And the question is, how does one characterize this state? Is there any special property that this state enjoys in comparison with a generic multipartite state. Okay, so here I have considered 3 regions. That is not important. You could consider many regions and ask what is the structure, what is the multipartite structure of the state. Okay.
So, Abhijit, can I ask?
Yes, please.
So, you're talking of a generic state, or you're talking of a special kinds of states?
No, a generic holographic state.
A generic holographic state. So you basically a typical geometry. That's what you're having.
Yeah. So here I taken the example of a vacuum state, but it could be a thermophile double state or a black hole state. Things of that.
But still these are special. I mean, it's you take a generic state would be a time dependent state, not an eigenstate of the Hamiltonian.
Okay, so let me say that I'm talking about a state that is described by a particular gravitational geometry on the dual side.
You're
not a microstate.
This Euclidean kind of. So maybe you're talking of states that are created by Euclidean path integral based on some operator insertions on this cap.
No, I mean every state is of that type. What I'm talking about are states which are described by geometry on the dual side. These are geometric states, if you wish, on the dual side. As opposed to, for example, overlap of vacuum plus vacuum and excitation. Or vacuum plus a black hole. You know, a priori, you could just talk about these states because it's a vector space. I can just sum anything I want. But I'm talking about, as I said, states that are dual to a geometry on the dual side.
Well, I don't know. I mean, it's not like all states can be created by Euclidean path integral. There was some discussion on that in some papers. But anyway, but I think I get your point. So it's like it's not superposition of gravitational geometries. We're only talking about those states that are particular gravitational geometry attached to.
Exactly.
Okay, thanks. Yes.
Okay. Good. And now, so this makes a multipartite state in the holographic theory. And the question is, how do you characterize it? And we will ask this question modulo local unitary transformations. Okay. So this then lets us talk about entanglement. Okay, because by definition, the state modulo local unitary transformations is what is captured by entanglement in the state. Okay, so this entanglement could be of bipartite nature or multipartite nature. Okay, for multipartite systems, you would have to mod out not just by local unitaries associated to 2 parties, but all the parties in question. Okay, and now, so then this question that I'm asking can depend, of course, also on the geometric properties, the geometric properties of the regions that I'm carving out. So in this case, I have these regions A and B and C, and what makes the state special may depend on whether A and B are small compared to B or not, things of that nature. So in fact, we know an answer to this question already. Okay, one answer, because, you know, there could be multiple answers to this question, you know, what makes a state special. But one answer we know already, namely, if you have a CFT state, let's say, again, let's take vacuum for illustration purposes, and let's carve out the regions as shown here, A, B, C, and C. Okay, now, for such a state, one can compute mutual information between A and B, is denoted like so, IAB. It's defined as SA plus SB minus SAB, where SA is the entanglement entropy of A. Okay, and we know that for general quantum state, this is a positive definite quantity, right? But for this holographic state, one can explicitly evaluate it using the Ryuta-Kanagi formula, which computes the entanglement entropy of a region. So let me just remind you of this formula. So I have a state defined on a circle. So you can think of this as a slice of the full geometry, meaning the boundary as well as the bulk geometry, I'm looking at a slice of a sphere, a solid sphere, from top. That's what I'm doing. And let's say I have region A and A complement. Then the Ryu-Takayanagi formula says that the entropy of A is equal to the area of this surface, R. Okay, or RT. So using this formula, one can compute the mutual information. So for example, let's take the case when A and B are sufficiently far away. In that case, SA will be given by this surface, SB will be given by this surface, and SAB will be just given by the union of these surfaces. So the areas would just add up. If you do the subtraction, you would get 0. So the point is that when A and B are sufficiently far away, a particular quantity which is generically positive definite, non-negative for a general quantum state becomes 0. So the holographic state, thought of as a tripartite state on ABC, starts saturating this inequality. So in that sense, the holographic state becomes special if A and B are sufficiently far away. Okay, so this is one example of what I mean, one answer to the question that I was asking, what makes the holographic state special is that the mutual information vanishes, or this inequality is saturated as A and B go away from each other. Okay, after sufficient, when they are sufficiently away from each other. Yes, go ahead, Ayan.
Yes, so you were mentioning this things far away, and you were also, of course, already told us that you want to look for cases where there's a single bulk geometry. But I mean, I'm just asking because I don't know myself. So, like, for example, you can think of putting like quantum matter inside, or some, I mean, you can still be semi-classical, or there could be some wormhole-like stuff that connects these two. So you could have some other Ryu-Takayanagi surfaces also, right? Right, in principle, that even though this A and B are far away.
Yes.
Yeah.
So the point is that, I mean, so when I said far away, I was sticking to this vacuum state. But if you have some exotic states,
yeah, that could be.
Then the conclusions may be different. But there is some region in the configuration space of the boundary regions where the inequality will be saturated.
Yes. Yes.
Okay. So that's what that's just what I mean. That in those regions of configuration space, you can characterize the holographic state saying that the mutual information between regions A and B vanishes. Okay.
This is actually what you're saying should be also true in general without holography, no? There's this statement as you made, that should not rely on the RT surfaces.
Yeah, but when exactly that happens, we know from holography we can calculate.
Yes, exactly.
At least for the states that have geometric duals.
Yes, that's true.
Now, general quantum theory, yes, I agree that you do expect that when the regions are far away, the mutual information should vanish. Yes, you do expect that because of locality, but you cannot quantitatively characterize it. When is it that you expect this? Exactly. Right?
Nowadays, people have understood in the vacuum. There are some work by this Cassini, Pablo Bueno, and all this group that they try to classify exactly this kind of issue. Like you take different regions and they look at the mutual or entanglement between different regions, and they try to, I think, understand what is the most general characterizations.
So this is for interacting theories or free theories?
I think general theories, yeah.
General theories, okay, would love to see that.
That is how they're trying to, in fact, they're trying to see if whether you can, it's like an alternative way of defining a quantum field theory. Instead of like using correlation functions, they try to do it like this, like take different regions and try to characterize the entanglement and see. I think they call it some different, I don't remember what exactly they call their program as, but they have set series of papers on this. So,
okay, yeah, would love to. Yeah, I'm not familiar with the series of papers, but would love to look at it.
Okay, all right.
Thanks a lot. Okay, so yeah, thank you. So as I was saying, at least for holographic states, we have quantitative characterization of when is it that this mutual information vanishes, and in that sense, it makes the state special. Now, this characterization is just given by a number that was positive for general state, and it vanished for when these holographic states when A and B are sufficiently away. So you may not be that impressed. But of course, it tells us much more about the state than just vanishing of a number, because you know that when mutual information vanishes, the density matrix on A and B factorizes. Okay, so IAB equal to 0 implies rho AB, which you obtain by tracing out C, factorizes. Now, this is, of course, an infinite dimensional specification of the state. You're saying something about an infinite dimensional rho AB, and that factorizes between two Hilbert spaces. So that's certainly an interesting characterization of the state. But as Ayan was saying, perhaps not that surprising, because even if you don't characterize it quantitatively, you do expect that general quantum states or general states in local quantum field theory should have this type of factorization if the regions A and B are sufficiently away from each other. Okay, so what else can we say about the state? Now, this question people have looked at, especially with the motivation of coming up with inequalities that are obeyed by holographic states. Okay, so this goes under the name of holographic entropic cone, where you use quantities that are constructed using the entropies of various regions. So you can take, so the way mutual information was a linear combination of entropies of the regions involved. So this SAB, of course, is C. So here you just have, the entropy of this plus this minus the entropy of C. So there's some linear combination of entropies that you consider. And you show that, and you show using the geometry of minimal surfaces that there is an inequality that this linear combination satisfies. Okay, so in that sense, and these inequalities are not necessarily obeyed by general quantum states. They are obeyed only by the holographic states only because the geometry of RT surfaces obey those inequalities. So that's one characterization of the multipartite structure of the holographic quantum states. But here I would like to make two remarks. One is that when you consider linear combinations of entropies of regions and take then that is not necessarily a characterization of multipartite structure of the states. Okay, in other words, there could exist states that are distinct, that differ from each other up to local unitaries that give the same entropies of all the regions. Okay, so one example that is usually given to illustrate this point is the following. So consider this. I will just take a simple example. Okay, so 3 qubits, and consider the following states: psi 1, which is a W state. Okay, so let me write this explicitly: 0, 0, 1 plus 1, 0, 0 plus 0, 1, 0. Okay, so this is what is usually known as the W state. And let's say another state, psi 2, which is 1 over square root 3. It's type of a GSZ state, but not the usual one. It's a little unbalanced one. Okay, so if this square root 2 was 1 and this was square root 2, so that the state is normalized, this would be the standard GSZ state. But this is a GSZ state weighted with different weights for 0, 0, 1, 0, and 1, 1, 1. So these two states are multipartite states on these qubits ABC. Now, these states you can check very quickly that the spectrum of all the density matrix that you can construct, rho A, rho B, and rho C, is the same for all the states, or for both these states. Okay, so if you are a bipartite person, a person who only wants to look at bipartite things, you would be concluding that these two states are equivalent to each other up to local unitaries, but that is not the case. Okay, and that can be seen by evaluating a genuinely multipartite measure or invariant. Okay, now this is not some mysterious invariant, not some complicated beast. In fact, as I will illustrate later soon, there's actually an infinite family of genuinely, what I'm calling genuinely multipartite invariants. and it's a very easy thing to construct, and one can evaluate it, and one can obtain, and one would obtain different answers for Psi1 and Psi2. Okay, and because it's a local unitary invariant, you conclude that these two states are different from each other under local unitary transformations. Okay, so this is just to show you that if you restrict yourself to only bipartite measures, such as linear combinations of entropies, so for example, because rho A, rho B, and rho C are identical to each other, any sort of entropy you would construct from it, let it be von Neumann entropy or any entropy, you would get the same answer. So you will not be able to probe the multipartite structure of the state. Okay, so that's one. Because all these inequalities come from that. Yes, go ahead.
So isn't there something like how much the strong subadditivity is violated or something else that can, there's usual entanglement measures cannot distinguish these two?
So strong subadditivity is also the statement about inequalities obeyed by certain combinations of entropies.
Yeah, so how much it is away from saturation, isn't that could be a measure to distinguish these two, or?
No, no. Because as I said, rho A, rho B, rho C, all the density matrices are identical. Identical meaning they have the same spectrum. Okay, so no matter what you compute from it, the entropies of A, entropy of B, entropy of C, and then the inequality of strong subadditivity would have it in some combination, that would be you would get the same answer for both.
Because you're saying that the spectrum of rho AB should also be the same as rho C because these are pure states. So so it should not matter. I think that's, is it? Or even
yeah,
if you
sure.
bipartite, yeah, so it doesn't matter. Whatever you do, it will give you the same.
No, but this is an example of 3 qubits. I don't have any example of multiple qubits, but I would imagine that you can write down states with the property that any density matrix that you can construct out of them has the same spectrum, but the states themselves are not related to each other by local unitaries.
Yeah, I see. So yeah, very interesting point. Okay.
Yes. Yeah. So that's why you have to kind of move towards some new type of measures that are invariant truly under local unit transformations, which can diagnose the distinction between Psi1 and Psi2. Okay, so that's one. That's one point that I wanted to make about this cone, because the cone usually is one looks at this entropic combinations of entropies. And another thing is that what makes holographic states special from the point of the cone is that they satisfy certain inequalities which general quantum states do not necessarily. Okay, so that's a very good characterization, although it is not as strong as the characterization that we saw earlier, which was vanishing of the mutual information, because one did not say that the holographic states obeyed a certain inequality, which was not expected of a general state, but rather it saturated an inequality. So it's an equality rather than inequality. So in that sense, it's a stronger characterization, which is what leads to this characterization in terms of factorization of the density matrix. Okay. So in that sense, one would like to get stronger characterizations of holographic states. Okay. So that's what I will do now. So because I motivated the study of invariants under local unitary transformations, we will go towards that. And because the story that I'm going to tell is a bit longish, I will try to not go into the details. In fact, at one place, we actually proved a mathematical theorem whose proof I will not be giving, but I'll just be stating the theorem and see what we learn from it. Okay.
Can I ask a question?
Yes, please.
So when you say local unitary transformations, do you mean like, in a sense, like gauge transformations where
No,
the unitary
I can write
vary?
down explicitly what I mean. So there's a state psi, right, which lives in HA, tensor HB, tensor HC. So what I mean is the following, that I want to take psi to psi prime, where psi prime is equal to UA tensor UB, tensor UC.
Right. Okay, that's what I meant. It's acting separately on each.
Exactly. Yeah.
Okay,
So
thanks.
physically, you can think of, usually when one talks about entanglement, etc., one thinks of Alice holding a qubit and a Bob holding a qubit, maybe Charlie holding another one, and then they can do local unit transformation in their lab. I mean, they can do much more, but let's say in particular they can do local unity transformation. So that's a unity transformation in their lab. That's what I'm calling local unity transformation. Something that can be done by different parties holding the quantum systems.
Right. I mean, in the context of unitary transformations on subregions of this boundary,
Yeah.
I mean, you could think of these like as a kind of a gauge freedom, right? If you think of taking smaller and smaller regions as you go from one region to
gauge
another region.
is a bit of a loaded word, right? Because we use word gauge for describing gauge theories. So I would rather not say that.
Sure. Okay, I understand.
Okay. All right. So let me move on to the discussion of local unitary invariance. Now, as I was saying, that we are interested in characterizing holographic states up to local unit transformations. It serves us well to look at local unitary invariants. So how does one go about constructing these invariants? Okay. So for illustration purposes, let's consider again a tripartite say psi with indices psi, I, j, and k. So one way to make local unitary invariants is to take a psi, right, which transforms in a trifundamental representation of different unitaries, and consider its complex conjugate psi bar, and that will transform in anti-trifundamental representation, and you just contract indices. But you should contract indices of party 1 with the party 1, Bra indices with the Ket indices of party 1, Bra indices of party 2 with Ket indices of party 2, and so on. So if you did that, clearly, if you did a local unity transformation, the U diagram factors coming from the Bra and the Ket will cancel, and you will get an invariant. Okay, so I just want to say that in order to construct local unity invariant, you just contract indices. Okay, the simplest such index contraction is done when you consider one copy of psi and another copy of psi. It's conjugate. I mean, if you want to contract indices, note that you need as many psi bars as psis. Okay, so in the simplest case, I have one psi and one psi bar, and if I just contract indices like so and some more these things here, then I will get an invariant. But of course, it is trivial because what I just made is a norm of the state. Okay, so the norm of the state, you can just normalize it to 1, so it does not is not very interesting. Now, of course, you can do more interesting things. The next thing that you can do is to construct 2 psis and 2 psi bars and contract indices, not I1 here like this, which would make just the product of norms, but rather, let's say what I've done here is I've contracted I1 to I1 and J1 to J1 to J1 here, and K1 to K1, and this I2 goes here, and J2, K2 go here. Okay, so as you can see, I've not contracted them in the same copy, but I've contracted them across copies, and this now makes a non-trivial invariant of local unitaries. Okay, but in this particular example, it's still not a totally non-trivial invariant, because note that the contraction of JK has been done in pair. Okay, so it is of course invariant under local unitaries, but it is invariant also under unitaries that scramble party 2 and 3, or whatever B and C, the ones that hold the J and K legs. Okay, so we don't want that. In order to construct genuine multipartite invariants, we want to contract in a way which do not take 2 types of indices together all the time. Okay, but as you can imagine, it's very simple. So now, given that these are the sort of invariants that we'll be working with, it is useful to introduce a graphical notation for index contractions. Okay, because with that, it becomes very easy to describe what we are doing. So let's denote psi as a blob, as a white dot with I, J, K legs. So this is psi, I, J, K. and a psi bar as this black dot with ijk lengths. So this invariant, which is the norm that we talked about, would be graphically represented like so. You have a white psi and a black psi bar, and you have this red. So red is the I index, blue is the J index, and black is the K index, and they're contracted like so. Okay, so this is just the notation for the norm. Now, this other non-trivial thing that I mentioned here was that was constructed by considering two psis and two psi bars. Okay, and the contraction was the first copies I was contracted with the first copies I, the same with the second copy, but the J and the K indices, which are the blue and the black indices, are contracted across copies. So this is the notation for this invariant. Okay, but as I was saying, from this graphical notation, it is very clear that the blue and the black line always go together. Okay, so even though this is invariant under local unitaries, it is actually invariant under a bigger group, namely a unitary acting on AB, a unitary acting on A, and unitary acting on BC together. We don't want that. We want to distinguish B and C. So that's why we don't want to take the black and the blue always together. Okay, so in fact, what we made is just trace rho squared. If you follow these contractions, it is easy to see what we made is just trace rho square, where rho is the row of this red party, or row of the black and blue party. Okay, so this is familiar as we know. Trace rho square, of course, is a good bipartite measure, but we wanted something tripartite. So the simplest non-trivial one that we can invariant that we can make, which does not take red and black together or any two parties together, is this one. It needs 3 copies of psis and 3 copies of psi bars, and the contraction is made as follows. So the black line, of course, I just contracted like this. So this you can do without loss of generality. You can, without loss of generality, for any one party, here I've chosen to be black party, you can just contract straight. And then the other 2 contractions, you can do any which way you want. Okay, but you have to make sure that the red is contracted with the red, the blue is contracted with the blue always. So here in this graph, you can see that none of these lines go together. So that's what makes it a purely tripartite invariant. Okay. Now, as you can imagine, if you have higher number of psi and psi bars, the number of such graphs that you can draw grows very fast. Okay. In fact, generically, the graph that you draw will not have the black and the blue, for example, always going together, right? They will just do their own thing. So in that sense, these bipartite invariants in this space of invariants are very, very special things, which we don't want to consider. So this is what I meant when I said that if you want to distinguish between psi 1 and psi 2, it's not that you have to compute some mysterious thing. You can compute any of these graphs, pretty much. A generic graph will not take all these lines together, and that value of graph will tell you that psi 1 and psi 2 are different from each other up to local unitary transformations. Okay, so those graphs will generically give you a genuine multi-partite invariant. So this will detect the difference between these isospectral states that I talked about. Isospectral because the spectrum of the same.
Abhijit,
okay. So now that we have, yes.
Abhijit, sorry. So about this example that earlier, these two having same tripartite is 3 qubit states. How will this distinguish them? Which one distinguishes them?
Oh, any of these things. So you can just compute any of these things as long as a pair does not go together. A black and blue does not go together, or red and black does not go together. Any graph of this type, you compute it and it will be different.
No, that can you, is there, so I don't know, maybe this is a theorem that would, I mean, is it, suppose I look at any 3 qubit state,
yes.
Will this be able to distinguish them? I mean, suppose you have any 3 qubit states that are the same bipartite. If you take any bipartite density matrix, it will be same for this 3 qubits. So the states are distinct apart from local unitaries. Will they, this one will distinguish them, or?
I mean, one guy generally will not make the distinction in all the cases, just because the dimensionality of the Hilbert space is much bigger than one, right? So. So that will not do, but you can consider, let's say, a set of these graphs, as many as which goes like the dimension of the space. Okay, then it will distinguish.
What I wanted to learn is essentially that you have introduced very new interesting measures, but is there one can prove that these are somehow, at least in certain cases, like for like three-party or something, whether one can prove that it is also sufficient to distinguish all?
Yes, but you have to consider multiple of them, not just this guy. This was an example.
Yeah.
So you can take this and
Yeah, sorry. I think I missed this part. So by distinguishing, you mean that, so I, define these invariants and then I act on the states by local unitaries, and then what I get will be different from what I start.
No, these are local unitary invariants, right?
Okay,
so the point of these quantities is that they will never change under local unitary transformations. So now you have these two states, psi1 and psi2, and you want to see whether they are equivalent to each other, whether you can go from one to the other by local unitary transformation or not, right? And naturally, one way to answer this is to calculate all the local unitary invariants that you can on these states. And if any one of them is different, you are sure that they are not related to each other by local unitary transformations. That's the idea. Okay.
So you created one of these graphs by using all the psis.
I made multiple copies of psis. So
So you So this is created by one psi1.
Yes.
And then you are saying that if psi1 and psi2 are related by local unitaries, then if you create the same thing with psi2s, that will be different from what you have.
Exactly. Yeah, you are not mixing psi1 and psi2 here. You just take a state, evaluate any of these things, and take the other state, evaluate any of these things, and see whether they are the same or not.
Okay, and how to see that this is a good measure for this distinction?
Well, you evaluate. So in the example that I gave you, just evaluate this guy, for example, and you will see different numbers.
So this, what Abhijit claims is that if you have three parties, then these three things that he talked about, this kind of different graphs will distinguish all 3-qubit states that are not related by local unitaries.
That is not the claim.
No, that's not the claim, right?
The claim is that in this particular case, this will distinguish it. Okay. But we also see that, if you construct it, if you construct other graphs like this, so for example, you can introduce, more of these things here. And like this. Okay. And then you can also start contracting now. So for example, you can now take this black guy and go here, right? So then this will become some other measure, some other invariant, right? A more complicated invariant. And as you can imagine, as you increase the number of replicas, so the number of psis and psi bars, I'm calling replicas. As you increase the number of replicas, you will get it will grow super fast. I mean, faster than factorial in the number of replicas.
Yeah, I understand what you said, Abhijit.
Okay, but so now I'm saying in that space, unless you give me your problem extremely finely tuned, it will be detected by one guy. Okay, any one guy. If you don't fine tune your question, then generically any one of these guys will detect it. But let's say you fine tune it so that this guy that I mentioned, that I said is identical. Then I can just look at another guy. Okay, there are billions of things that I can look at. And one of them will certainly be different. And you don't even have to look at zillions of things. You probably have to look at things that the number of things should be just like, you can probably find a set of dimension worth of invariants, any dimension worth of invariants, a number of invariants you can look at, and one of them will be different for sure.
Yeah, I understand what you are saying. I'm just saying that suppose if I have only a 3-qubit state, there should be some finite subset I can identify that will distinguish all 3-qubit.
Yes,
I see.
Yeah.
Because of course.
So that exactly. So I'm not necessarily saying that this one guy will do it, because It may be that, if you just look at the space of states, right? Modulo local unitaries, that space of states is not one-dimensional. It is actually, in the case of 3 qubits, it's 6-dimensional. Now you have one function on a 6-dimensional space, right? Now clearly there will be equipotentials, which will be 5-dimensional. So if you want to distinguish points in this 6-dimensional space, you would have to look at 6 functions, and generically there's one of those will be different. That's what I mean by you just have to look at those particular finite dimensional sets. So in this case, actually, now that I think of it, in the 3 qubit case, I know that this space is 6-dimensional. So you just have to look at any set of these invariants which has any set with 6 of these things you have to look at.
Okay.
Yes.
So like, just to make sure, so I suppose, going back to your previous original graph that you had, then so there, so is there any way to graphically understand that, now instead of this invariant, if I use U acting on psi and then create the graph will look different, which will help me distinguish between...
No, the graph will not be different. So another way to see that this is local unitary invariant is you can write U here. Let's say UA here, UB here, UC here, and similarly here. And on this side there will be U dagger, and along the lines they will all will cancel, and this will produce a local unitary invariant. That's why we contract indices, right? That U and U dagger cancel, and you get invariant.
Yeah. So this is no, of course. I mean, this entire thing, as you said, is a local unitary invariant. Sorry, I'm not yet understanding like how this graph is able to distinguish between psi 1 and psi 2.
Because psi 1 and psi 2 are not related to each other by local unitary invariants, right? So if something is not related to each other by local invariants, local unitary transformation, then if you compute local unitary invariants, they should be different on them, right?
Oh, okay.
So
you are basically creating a invariant which, because you have like here 3 qubit states and you have 3 copies, and that's why it is able to...
No, this 3 qubit has nothing to do with the 3 copies.
Okay.
It could have 4 copies also, then also it will distinguish.
But minimum of the same copies, minimum?
Not necessarily. In this case, it is the case because you needed actually 3 of the replicas so that to write down this non-trivial graph. Because if you had smaller number, you necessarily have to do repetition. Yeah, but let's say that is not necessarily always the case. No, I don't think so. If you have 4 qubits, I think you can make non-trivial invariants already with 3 replicas, I think.
I mean, very nice. So generic, very nice question. So generically, it is should be easy to distinguish, right? 2 states which are not local unitary equivalent.
You just compute this.
Yeah. So like naively, I would have thought that any sort of, local unitary invariant operator I can construct, out of psi 1, that thing will be different for psi 2 if psi 1 and psi 2 are not local unitary.
Yeah, that is the point that I am also making. Nothing else.
But Jati, he was in the beginning of the seminar. So Abhijit was giving examples of 2 3 qubit states which are not related by local unitaries. But if you look at standard entanglement measures, they would give you the same answer. You cannot distinguish them, and this is a motivation for creating this different new measures that he's talking about. Actually.
Exactly.
So entanglements are not good measures. Is that what you're saying?
That's what he was saying.
By entanglement, you mean entanglement entropy and the Renyi entropy.
Entanglement entropy.
Yes, then that's what I'm saying.
But these invariants are like the psi bar type thing. that you have constructed before. Psi
Yeah,
IJK.
usual entanglement measures also, Renyi entropies can also be made out of psi bar like this.
Okay.
Yeah,
I think
perhaps we should move ahead. Today we have a cutoff at 12:30. So
yeah. Okay. Sorry about that. Yeah.
Okay, fine. Good. Thank you. So now, as I was saying, such invariants, which are genuinely multipartite invariants, will detect the difference also between the isospectral states. Psi1 and Psi2, the examples that I give. But now, this discussion makes it clear that there is a zoo of such invariants. Okay, so what is it that we want to pick? So this is guided by the requirement that we need to be able to calculate it for holographic states. Okay, and this actually dramatically reduces the possibilities. So without going through the classification and arguing why is it that a certain thing is calculable and why is it that certain thing is not calculable, let me just give you the thing that is calculable for holographic states. Okay, and it is the following. So before that, let me introduce one more slight notation, namely the notation for the density matrix. So I have psi and psi bar, as you say, as one says that if you contract one of the parties, you get a density matrix on the remaining two. So what I've done here is that I've contracted the party C and party A and B, they have indices left open. Now I get a row, which you can think of as a matrix from HA tensor HB to HA tensor HB. Okay, where I prime are the indices of HA and J prime are the indices of HB. Okay, graphically, in the previous notation, I had this as psi, this as psi bar. I have contracted the black party, this one, and now I have open indices for the red, two open indices for the red party, but those indices are one is incoming and the other is outgoing, and two indices for the blue party, again one is incoming, one is outgoing. Okay, so this is the picture that I got for the density matrix. Now I will, because I will be working only with density matrices, I will introduce this notation for it. So this black dot is a density matrix, and two blue arrows incoming and outgoing, two red arrows incoming and outgoing. And in fact, let me further simplify this by denoting this set of two arrows of incoming, outgoing red things as an undirected edge, like so. And two arrows of blue incoming and outgoing as an undirected edge, like so. So this would be my density matrix, where the red edge should be thought of as a set of two edges, incoming and outgoing. Okay, and I'm allowed to do contractions of the red edge like so. So I can do red edge going from here and coming here and contracting it here, and which means that I'm contracting in this way with another density matrix. Okay, so in this way I can contract red edges and make graphs out of this edge with the vertex being rho. Okay, so now I'm ready to give you what the measure that is nice from a holographic point of view, and it is this. So I define a measure E psi jk as this guy, where each vertex is a density matrix. Okay, so here I have 4 density matrices. So number of psis is 4, number of psi bars is 4. In this picture, this was 3 and 3. Okay, so you could of course go back to the psi and psi bar picture and rewrite this diagram, but I'll just keep it like so because it will illustrate, because this will be useful for generalizing it to higher number of parties. Okay, so this is a measure which requires 4 replicas, and that is clear from the fact that it is 4 vertices, 4 row vertices. Now, so here you can see that, yeah.
So you're looking at complete permutation in what kind of symmetry? Are you looking at all possible permutation symmetries, or like?
Yeah, just 1 second. I'm not yet this line here. So one point that I want to make is that this invariant here, although it looks like I have traced out the black party, right, and made this invariant from the red and the blue party, the black party seems to be treated differently. But if you now take this and rewrite it in terms of psi and psi bars, you can see that the resulting graph has a permutation invariance as I permute red, blue, and black. So it is actually permutation invariant under all the parties, the 3 parties involved. this graph obscures that symmetry, but it is symmetric. Okay, so that's why I say symmetric in all the parties. Yes, Ayan, can you ask this question?
Yeah. So yeah, you probably almost answered it. When you say that it is permutation symmetry, means that you look at all the three colors that you put in,
Yes.
and you say that if I permute any of them, I get the same graph. But then you could do the permutation. So what I'm confused about this definition is that you can. So if you do a permutation on one particular vertex, you have to do a corresponding unique permutation everywhere. Is it always that should be the case always?
Permutation of the parties on one vertex.
So yeah, I'm not. Maybe I don't understand. Yeah. So you're saying that this.
This is just a graph, right? A graph. You have a graph of red, black, and blue edges. Now you just permute the colors and you get the same graph. That's the statement.
Oh, okay, I see. So it's a global permutation, not
global permutation.
Okay, so it's a global one, and you say that. Okay, so when so you're looking at this. Okay, yeah. I see.
So now let me talk about yet another permutation, namely this. If you take this plane and reflect about this plane, this is also symmetry of this graph. Okay, this is different from permutation of parties. This is now permutation. This is the symmetry of the graph itself. Okay. So this symmetry of the graph is what I call the replica symmetry. So for example, in this case, the replica symmetry is this Z2 across this axis and this Z2, which is across this red, which flips the red axis. Okay. So the permutation symmetry of this measure is Z2 times Z2. Okay, so now this suggests a natural generalization for higher number of parties. If we had, let's say, one more party, let's say yellow party, what you would do is you make a cube with 8 vertices. One face of this would be this one. Another, the face that is next to it would also be the same one, but the edges connecting it would be all yellow. Okay, and now you can see that this, if you color the cube edges like so, it is symmetric under permutation of all these colors. And moreover, the replica symmetry, which is the symmetry of this cube, is Z2 times Z2 times Z2. Okay. And similarly, if you have one more party, it would be a 4D cube, and so on and so forth. So in this sense, this is the definition of a measure which is valid for any number of parties. And as I was saying, it has permutation symmetry, which is Z2 to the power Q minus 1. Okay. So this ends the discussion of the definition.
For this constructions of this, because in principle, of course, you could you can always construct a corresponding manifold, and I guess you can always compute the partition function for any one of your measures, right?
So we will talk about that now. But here it was just this abstract definition of what I mean by the measure.
Okay, so but you want to
now we will get QFT.
So in that context, I have a question. Like, if you restrict yourself to such symmetries, some extra symmetric measures, how much they are going to do the job for generic? So they might be good for...
Let me get to that, Ayan.
Okay.
I think it will. Yeah, that is the appropriate place to ask.
Also, just to make sure, so far holography played what role?
0.
No role, right?
No role.
Yeah. Okay.
Yeah. So the more discussion was, the way I motivated it is to argue that I need a genuine multipartite measure. We discussed that, and now I'm just giving you the answer for a measure which is useful for holographic
clarification. I want clarification. So basically, when you make this invariant xi, so you wanted to tell that the vertex are black and then the edges are like blue and red. So you can also make vertex like blue and the edges like the other two color and the other way around. So you can make all sort of permutation where the vertex could be either black or red or blue, right? And yes, they all will give rise to the same measure.
Exactly.
Okay. Okay. Fine. Yeah, I get it. Thank you.
Yeah. Okay. Now, okay. So now we have defined these measures, and they're defined because I did not tell you how it comes about, but these turn out to be the nice measures. These are the measures that that can be calculated in holographic theory. So I will not now I will move to the discussion of these measures in QFT and go towards how one would go ahead and compute these measures. So now in QFT, the state psi ijk, let's say, let's take an example of again, sorry, but before that, let me just say the following. Actually, so this defines what I call the E invariant, and the measure that turns out to have nice properties is this S, which is simply related to E by taking a log, putting a minus sign, dividing by 2 to the power of Q minus 2. Okay, so this turns out to be a nice measure to look at. So we will always look at this S, which is basically log of E. Okay, so now we will compute S in quantum field theory. So psi ijk, again, for illustration purposes, I have taken a 2D state in a vacuum. You do the path integral to produce this state, and you have these 3 regions, A, B, C, and these indices ijk correspond to the states on A, B, C. Okay, now, so this produces a state on 3 parties, the tripartite state that we have been talking about. Now, similarly, psi bar is basically the same type of construction. You just flip the sphere over and construct a ket. So this constructs a bra and this constructs a ket. And the regions, of course, are the same, which are the ones that appear in the equator here. Equator is common on both sides. Okay, so now we want to construct these measures by contraction. And then this is the nice thing about the way we define measures in terms of taking replicas and contraction, because now it is very clear what we need to do in quantum field theory. So remember, you had the way I constructed it is I had a bunch of psis, I put them in the bottom row, and a bunch of psi bars which I put in the top row. So similarly, I start with putting the bottom hemisphere like so, and the top hemisphere like so. So far, they are far from each other. And as I contract things, I start gluing the regions. So if I contract this party, I just glue this region here to this region here. Okay. And when I contract this party to this party, I'm doing this region. Maybe I should do red. This region to this region. And when I contract this party here, that means I'm contracting this blue stuff here to this blue stuff. And similarly, the rest of the contractions can be understood in geometry. So in this way, what is obtained is some complicated manifold, replicated manifold M, on which your quantum field theory lives. Okay. And now, because this measure enjoyed this replica symmetry, which was Z2 to the power Q minus 1, the replicated manifold, if you look at the background fields on the replicated manifold, they will also enjoy this symmetry. They will be, so this background field on these manifolds would be replica symmetric, namely symmetric under Z2 to the power Q minus 1. Yeah, I think at this point, probably Ayan, your question is better placed.
Yeah, no, my question was essentially that I thought that irrespective of requiring this excess symmetry, you should be able to compute it in quantum field theory anyway. So what was the role of the extra symmetry that you were trying to impose?
Yes, so we will go there. Yes. Now we would be able to compute in quantum field theory. I don't know. I mean, quantum field theory is a difficult thing. I don't know how one makes general calculations like that. But we will see the measure is constructed carefully in a way that I can calculate it in holographic theories. Okay, so this is the
my basic thing was that you're trying to have these replicas, and then you're making some identifications, right? And then these identifications, with that you will get some manifold, which could be not of the right property. It may not have the manifold may not have the right replica, whatever. It might not have the replica symmetry or something, because you wanted a permutation symmetry between the different parties and all. So I don't know. I mean, in principle, one can define it, or is there some obstruction to defining the?
No, you can define all these things. There's no problem in defining anything.
I'm saying, so you take any arbitrary
carefully if you want to compute it.
Okay, no, that's a separate issue. But I'm saying that at least you can define the corresponding manifold.
You said you can compute it easily in quantum theory. Yes, you can define the no issue whatsoever in defining any of these things. And this prescription makes it clear how you go about it. You have a bunch of psis, you just take a bunch of hemispheres, and psi bars, take a bunch of top hemispheres, and the way indices are contracted, you just glue the regions together. And this prescription will produce for you some manifold. It will be extremely complicated beast in general. Okay. And the only thing you would be able to say is that this measure should be a partition function of this, and that's it. But now what we will do is, because we have constructed these things carefully, we can do more and we can compute this, okay, to some extent.
Yeah, but I see. But in any case, I mean, even in the holographic case also, you can fill in any, like define the corresponding holographic partition function, right? I mean, there should not be any obstruction as such. I mean, I thought that in defining at least, I thought is whether you can easily compute.
In defining these things, there is no abstraction whatsoever.
Yeah, okay. No, but I was thinking the reason I was got confused because you said that there is something special about for that only certain measures work holographically. So this is why I got confused.
Not work, can compute. Can compute.
Okay. Yeah. Computation might be hard in principle.
Yeah.
Okay.
So these measures have been carefully constructed so that it allows for a computation.
I see.
So that
okay.
we can say certain things.
Okay. All right.
Otherwise, we would have to stop at this statement here.
Okay.
Okay, so now actually, one would like to go ahead and compute this, right? I mean, in general, this looks unwieldy. How would one go about computing it? So here we will use the fact that first of all, our measures are symmetric, and second of all, we don't want to compute in general quantum field theory. We want to compute in holographic quantum field. So this is where the holography now enters, and we will follow the methods used by Liukowitz-Maldacena to prove Ryuta energy formula. Okay, so the idea is the following: as I am correctly hinted at, the way you want to do this calculation for holographic theories is by computing the action of the bulk solution, dominant bulk solution, because that's what will give you the partition function in the large C limit. Okay, so in order to do that, I have to first find the bulk solution B, which fills in the boundary M. Okay, and then I have to compute its action, the gravitational action on that bulk solution. Okay, so far so good. I cannot quite do this for a general B, but now comes this fact that there is a replica symmetry for the boundary manifold. Now, whether the bulk also enjoys that replica symmetry or not is a non-trivial question. Okay, if you construct measures with replica symmetry, there are of course other measures that you can construct which have lots and lots of replica symmetry. For those things, bulk may not have replica symmetry. But for this particular class of things that I talked about, bulk does have replica symmetry. Okay, so for that case, we have bulk, which is replica symmetric, and then we go ahead and orbifold by this symmetry. And the nice thing about that is that if you look at the boundary, when you orbifold, the boundary comes back to the unreplicated manifold. So that's kind of a nice thing about this orbifold. Now you don't have to worry, you don't have to think about these extremely complicated looking boundaries. The boundary is back to itself, which is a sphere. On the bulk, however, it's complicated, but that can also be tracked, what happens on the bulk. So without going into details, so the details you can find in these papers that I listed in the beginning, you can show that when you orbifold, what you get, as I said, the boundary is back to original boundary, but in the bulk, you don't go back to the original bulk solution, of course. What you get is this locus of singularities that stretches from the boundary points of the two regions. So there will be three of them in these three cases, in the case of three intervals. And so there's no reason this should be blue. And then there is a locus of singularities that stretches and meets and then that is anchored on these three boundary points which meet in the bulk like this. And the point is that the singularity angle here is pi. The conical angle around each conical singularity that you see is pi. Instead of 2 pi, which would have made it smooth, you have a conical singularity with a transverse angle pi, and these three singular loci meet each other in the bulk like so. So you can look at it from the top. The picture that you get is this, and this is the three singular loci meeting each other in the center. Okay, so subject to this boundary condition, subject to the boundary condition that you want to have a locus of conical singularities with conical angle pi meeting each other in the boundary, you have to solve the Einstein's equation to find this bulk, B tilde. Okay, and once you find that bulk B tilde, which is the orbifold geometry, its action is this measure S that we defined. Okay, is this clear? At least the statement. I did not go through the derivation, but at least the statement is clear.
Yeah, I think I understand the statement. The criteria is that essentially you want after the orbifolding with all the symmetries, you should have a single boundary.
Yes, exactly. That's one of the criteria. Yes.
But I didn't follow why you will always have in the bulk also this will go through, that you will have that you will have a locus, or like you said, that there will be some extremal or some special surface, I think, that you wanted to hint at, where it will.
Well, so this is the locus of conical singularities looks like this. So you can think of this as some surface traced out by a heavy brane. That's one way of thinking about it. That there is a brane with a large tension which back reacts in the geometry and is anchored on the boundary points like this.
Are you assuming replica symmetric bulk?
Yes, yes.
Okay, then it
important. For this particular class of problems, I mean for this particular class of measures, for 2 dimensions, you don't need this assumption. Probably in higher dimensions also you don't need this assumption, because one can show that the bulk has to be replica symmetric. Okay, for 2 dimensions you can certainly show that the bulk has to be replica symmetric, and then this has to be the case, that the solution must look like this with conical intersections like that.
Yes, and each in the CFT, the corresponding CFT calculation, you put some twist operators, and you have a single boundary, and at the 3 locations that you mentioned, the corresponding CFT calculation.
Yes,
right. Exactly. But it is, and just my question is now that is it like saying that you have from the CFT point of view, it is like multiple correlation functions of. So I'm just trying to understand, like you made an initial statement, your motivation was that to distinguish it from something that is purely not entanglement entropy-like. What I'm trying to understand from the CFT point of view, what exactly new you have achieved? Like you have 3 twist operators now, and
well, when you just say twist operators, they are not characterized, right? You have to say twist operator corresponding to which permutation.
Yes, of course.
So for entanglement entropy, those labels on the twist operators have a certain form.
Yes. Okay.
Right? But the twist operators that are entering here, they have different form. Okay.
Yes.
In that sense, they are different.
Okay. Thanks. Yeah, that was what I. Okay, thank you.
Yeah. Okay. Good. So now, this picture generalizes for a higher number of parties. Let me not worry about the colors a little bit. So let me just say, if I have, let's say, 4 parties, this picture generalizes, and the dual turns out to be again the same idea, that you have a locus of conical singularities. Okay, and the solution should be on shell. So you have to minimize this brane, minimize the action coming from this brane. So that's why you get a picture. The locus of conical singularities looks like so. Okay, so where each of these lines that I'm drawing stands for conical singularity with angle pi. Okay, and this generalizes to even higher number of parties, where you have to draw a minimum tree, which connects to all the boundary points, all the points that are the boundary points of the regions of interest of the boundary. Okay, and the statement is then that the measure that we talked about, S, is the action of this gravitational solution. Okay, so good. So this particular set of measures, this is what you can say. This is the best you can say. Computing this action is a bit difficult in general, but for 2D CFTs, this can be computed, at least in the tripartite case. But we will not concern ourselves with the computation of this. I mean, the reason that I'm saying that the computation is difficult, because these are singularities, okay? And you have to solve for this back-reacted solution. That's why it is complicated. what one can try to do to make this more computable is, instead of the class of measures that I considered, you can construct a family of such measures. I will not go into that, okay, which will be labeled by an integer n. So this, if you wish, would be the generalization of the second Renyi entropy, because holographically, when you compute the second Renyi entropy in the bipartite case, that is also given almost by the RT surface, but instead of the RT surface, you have a conical locus, you have a singularity locus of conical singularity pi. So this is exactly the generalization of the second Renyi entropy. So the way to go to RT surface from this point of view is to construct higher and the higher family of measures, where you have trace rho to the n, which is labeled by n, and then take n to 1. So a similar type of thing one can try to do. There are subtleties in this procedure, but if this analytic continuation can be done at n equal to 1, you will find a very similar picture, except that instead of conical singularity, you will have a probe brane, a brane that will not back react in the geometry. And in that case, this will be a very simple calculation in the bulk, because now you don't have to solve for a new bulk solution. You simply have to minimize the area of this network in the bulk and calculate the area, in this case the length. Okay, so that becomes as easy as the calculation of the RT surface. But for now, because that involves analytic continuation, I don't want to go there. I just want to restrict myself to the discussion of these measures. Okay. So now, even though you cannot calculate it, you can it turns out that you can make some non-trivial statements about this. Okay. And before we go there, before we see what sort of statements you can make, let me introduce one notion of coarse-graining. Okay. So by coarse-graining, I mean the following. So it's not quite, so during the announcement, he said RG, but it's not quite about RG, but it's kind of related to that. It's the following. So you can consider a q-partite state psi q, let's say with a subscript q, which makes clear that there are q parties in the game. But now you can bring two parties together, Alice and Bob together. Okay, what I mean by that is, now you let the unitary operator that acts on both the parties also act on the state. Okay, on AB, not just A separately, B separately, but you bring that together and you allow for unitary operators scrambling the parties A and B together. And then this state can be thought of as a q-1 partite state, because you brought two parties together. So in the case of quantum field theory, you have these regions, and now you identify the regions. So meaning, if you have a region A and a B, you mix them together and make a bigger region by identifying these regions. Okay, so this is a procedure that you can do for any q-partite state. You just identify two parties and make a q-1 partite state. Okay, now the measure that they define can be evaluated on any q-partite state. So you can evaluate it before identification and you can evaluate it after identification. And what is the difference? Well, the difference is this. As I said, for the case of, let's say, q equal to 4, I had a cube, a cubical measure, which looks like this. Okay, but now when I identify red and black party, these two guys are now thought of as a single party. So all the lines that I draw for them should go always together. So now this is a three-partite state, and the measure for that is a square. But now the square edge has these red and black parties going together. So this is what I mean by the measure, how it behaves under coarse-graining. So coarse-graining itself, by that I mean a psi q going to psi q-1, and how the measure changes under coarse-graining is that you compute the q-partite measure for this state and q-1 partite measure for this state, and this is what I call the coarse-graining of the measure, or the measure under the coarse-graining, how the measure changes under the coarse-graining of psi. Okay, now it turns out that the measures decrease monotonically under coarse-graining. So as you coarse-grain q to q-1, these measures that you compute on them. So for first, you have to compute a q-partite measure. Second, you have to compute a q-1 partite measure. So this is somewhat of a non-trivial theorem that we proved, that the measures are monotonically decreasing. Okay. So this is the theorem that I was referring to. Proof I will not be giving. Yes.
About the coarse-graining operation. So is this coarse-graining operation can be classified as a CPTP map of some kind?
It's much simpler than that, because usually, one talks about CPTP map on a given party, right? Here you just bringing them together, nothing else.
Yeah, but usually that, like for example, relative entropy, what people are worried about, like you take any entropy measure, whether it is monotonic under CPTP, and this is a question that people also ask.
Okay, I see. Yeah. So that's that's like an orthogonal type of thing that you can worry about. So you can worry about what happens if a party starts doing the thing that you say CPTP, or another way to say that is an LOCC operation. Right? LOCC, I guess it's a bit stronger than that, but yeah, so you can ask that also. What happens to the measure under LOCC operations, CPTP maps, as we say. And although I'm not, this I think of as a totally different aspect of this, and I have not found any holographic reasons to ask this question, but it's a very good and valid question, I think. And we also proved a theorem which says that this SQ is monotonically decreasing under LOCC. But because it is not relevant to this discussion, I was not going to say that.
Oh, I see. But what exactly you mean by this? You mean this block decimation like thing that people do under RG? Here, is
block
it that
decimation? I don't
mean,
know.
like you take the average of two. So I didn't quite understand this coarse-graining that you're defining.
Yeah, the coarse-graining that I'm defining is just that you have Q-partite state. You just think of it as a Q-1 partite state by bringing two parties together. That's it.
So it is not really a coarse-graining in that sense. It's just simply a transformation.
That's why I'm saying that I think of the CPTP stuff as a different thing and this thing as a different thing.
Yes, exactly. So it's not really a CPTP map of any kind. It's simply a graph transformation, which you're calling coarse-graining now.
Yes.
Okay.
But I'm saying furthermore that we did consider this question also, the question that you are asking.
I see.
And we found that it is monotonic under that CPTP map also. But it is not relevant to this discussion.
Okay.
So anyway, this is the inequality that we proved that the measure obeys under coarse-graining. It's involved the proof is involved, but so let me not go into that. Let me just state this theorem for now, that this entropy, this quantity S is monotonic under coarse-graining. Okay. Now one can ask this question for holographic states. If this is true in general, if this inequality holds in general, can we check that it holds for holographic states? Now that we know that this S quantity for holographic states is computed by a gravitational action for some conical solution, can I check that this holds? Okay, so let's ask this question. So consider this holographic picture where you have parties A, B, C, D, okay, and the B tilde that computes, whose action computes this SQ is a manifold with this set of singularities. Now let's coarse-grain, meaning let's identify the two parties. So now I'm identifying B and D. When they are identified as the same party, there is no reason for this middle line to exist. So now the new solution does not have this conical singularity that separates B and D. So you just have these conical singularities. And the question is whether the action of this guy is greater than the action of this guy. That if it is so, then that would be a check of this inequality for holographic case. And using what is called the Schlafly formula, I'm already a little bit getting late, so let me not go into the details of what this is. But this is basically a formula which relates the action of the gravitational solution to in two dimensions. I should say in 3 dimensions. And this bulk is 3 dimension. For 3-dimensional hyperbolic manifolds, it relates the volume. For 3-dimensional hyperbolic manifolds, the action is basically the volume of the manifold. So mathematically, what this Schlafly formula does, it relates the volume of the manifold to the area of this conical singularities and the cone angle around those singularities. Okay, so using this Schlafly formula, one can show that the action of this B1 orbifold and B2 orbifold, is indeed greater than the action for the B2 orbifold. Okay, so this verifies this inequality that is supposed to be true in general, that it holds also for holographic states. Okay, so that's a nice and satisfactory check. But now let's go back to the question that I asked in the beginning of the talk. What makes the holographic state special? So now we have all the tools to answer this. At the example that I gave suggested that the holographic states are not so special because, the actions also obey inequality as any quantum state would. But now let's do a slightly different thing. So let's consider B1, there's the first state exactly same as before. You have these parties A, B, C, D. And previously what we did is to identify B with D. That's what gave us this. But let's identify A with C. Okay, so that's what we'll do, A and C. Now, because A and C are far away from each other here, I mean, in the sense that there is this singular locus here, if you follow through the prescription, it turns out that even though U and A and C are identified, so here I written A and A itself, the conical locus that is dual to this measure is still the same as before. Okay. So here we have orbifold B1 tilde, and here a priori it could be different, but in this case, because these A and A don't talk to each other because of this wall, the holographic dual ends up being the same as this. So that's why their actions are the same. So in that sense, the inequality that we had for general quantum states is saturated for holographic states. So whenever in this network, whenever this tree diagram, you consider regions that are not separated from each other by walls, the way, for example, D and B are separated. They are separated from each other by wall. However, while A and C, they are not separated each other from a wall. Okay. If you consider regions that are not separated from each other by a wall, and you identify those regions, that the gravitational solution that is dual to the multipartite measure S is the same. So that's why the measure itself is also the same, because the measure is supposed to be the action of that gravitational solution. Okay, so you can see that a holographic states saturates a number of these inequalities. This is a general inequality. This is an inequality that a general quantum state should hold, should satisfy. And as promised, I showed that holographic states saturate a number of these inequalities. So in this sense, these measures help you distinguish holographic states from other states, from other general multipartite states. Okay. Now let me say a little bit more about this.
But
yes.
You can, I mean, one can actually do this computation in CFT also, right? With twist operators and check, whether what is.
You can set it up with the twist operators, but doing this calculation is difficult, right? How would you compute correlation function twist operators?
Yeah, it will be a hard computation, but is it? I mean, it could be.
I don't even know how we would go about doing it.
Why is it? In a CFT, you cannot modify. You cannot pose it as a CFT problem using.
You can pose it certainly, but I mean, the question is if you can make progress. I cannot see how you can make progress.
Twist operators, of course, usually have good OPs, and I mean, you can. This is easier in a way. Of course, if you do the analytic continuation, it might be hard, but I'm saying you don't have to do it analytic continuation.
I mean, it would be wonderful if someone could do it, but I personally cannot see how it can be done.
I think it is hard, you say.
Because I mean, one way to quickly see that is that it's not a universal answer. Because if you set up this twist operator business and you replicate the manifold, you get a higher genus surface. And when you have higher genus surface, partition function, a higher genus surface is difficult to evaluate because all sorts of junk runs in the loops. So,
yes,
I don't know how in general this can be done. Maybe, I mean, maybe not calculation, but maybe one can show that these equalities, something about these inequalities. I don't know. Yeah, I don't know how one will do that, but it would be interesting to explore, I guess. But I just don't have a beginning point to. I don't have a hint as to why this would be doable or. But if I see some hint, it would be very nice.
But then in the holography, how you can go a little bit away from Nazi or something, I don't know. So I'm just trying to understand like what exactly makes this saturation work, and that's what I was. Is it the Nazi limit or is it something more?
Yeah, good question. Good question. Yeah, I don't know. So this is certainly what makes holographic state special. Now, when you go away from large C, so one extreme case where this is doable, but this could be doable is in the case of free theories, for example. Right? In free theories, I think one can certainly try to do this. Okay, and there you can ask all these questions. What happens to these inequalities? I suspect the following, that there might be these inequalities that are saturated, but for different configuration of regions, maybe very tiny parts of the configuration space, meaning when the regions are very small or something. But for holographic states, this happens even when the regions are big. Yeah, I don't. Yeah, I agree. I agree. This is a very good question to understand why exactly this is happening. I think it is very interesting, and I think it goes towards, as I will just comment now, it also goes towards understanding local nature of ADS CFT correspondence.
Yeah, I think free field theories could be a good computation to do, just to contrast it. And yeah.
Yes, I agree with that. But general CFTs, I don't know. Even 2D. Okay, so let me make one more comment about this. So when we looked at this vanishing of mutual information, I emphasize that this, if you just look at it this way, then it looks like a vanishing of a number. But we know that it implies that the density matrix itself, so infinite dimensional density matrix, factorizes into rho A, rho B. Okay, so can one say something? And this is, of course, a more concrete characterization of the state, because we are really making a statement about the state. It doesn't even have to be locally unitary invariant. Well, okay, so this statement itself is unitary invariant under the unitary acting on C, but is not quite invariant under unitary acting on A and B separately. But nevertheless, one would try to one would like to have some sort of a general statement of this sort. What can we say about the state itself rather than saying something about a number? And in fact, we showed, when we proved this theorem, we also found out the conditions that are necessary for saturation of these inequalities. And those conditions are the following. So instead of this factorization of the density matrix on AB, it turns out that this saturation occurs if and only if what we call the transfer matrix factorizes. So in the case of this tripartite state, the transfer matrix is defined like so. It just has a one row and one set of A indices, one set of B indices. And this factorizes like this. So in this case, this statement is, this transfer matrix is actually just the density matrix. So this is the statement of density matrix factorizing. So this inequality for the case of tripartite state is just a familiar, this familiar inequality, which is a vanishing of mutual information. So this is kind of nice, that whenever that mutual information is saturated, you know that the density matrix factorizes like this. But now for higher number of parties, it becomes non-trivial. So you can consider a state with 4 parties, and there what factorizes is not some sort of a density matrix, but rather the transfer matrix, which you have to make by considering 2 copies of rho. So this is the vertex. This is one part of this cube that entered in making the measure. So the measure itself was a cube. I'm just looking at one edge of this cube with these 2 indices dangling. So this is what we call the transfer matrix. And now, because there are 2 sets of red guys, this actually is a matrix on 2 copies of A and 2 copies of B. Okay, so you can think of this as a T A prime, B B prime. And the statement is that the saturation of this inequality that I talked about corresponds to the factorization of this transfer matrix into the A parties and the B parties separately. And similar statements hold also for a higher number of parties.
Abhijit,
this statement,
do you have an example of a 3-qubit state where this can be, that this factorization works?
Yeah, so this 3-qubit state, you just have this, okay? But for 4-qubit state, it becomes non-trivial.
Yeah, okay. Some example, sorry, I wanted to ask for a 4-qubit
state. Yeah, good question. We have an example. No, I don't think we do. No, I don't have any example. You can numerically construct these things. I mean, you can just run your computer and go towards the minimize this inequality and try to go towards 0. So you can do good numerical approximation, obtain a state which saturates this inequality. So this equation holds as an approximate equation. But analytically, we don't have an example of such things. But I think it would be very instructive to find an example idea.
Yeah, so I was trying to understand how typical are such states in 4-qubit, and how less typical, whether it's a measure of such.
Good question. Yeah, I think these are all very good questions. Yeah, we don't have an answer. Okay. So now this statement is at the level of this transfer matrix, but it would be nice to see what, it's partly kind of what you're saying, that it would be nice to see what this means for a single copy of the state itself, rather than some transfer matrix factorizing. Okay, so I think it would be very interesting to figure that out, what it means for a single state. Yeah. Okay, so before I end, let me just mention one small thing in which I will not go into too much detail. So as we saw for this, if I did not have any quantum corrections to the bulk, the CFT S, this measure S in CFT, is given by the gravitational action. And just like in the case of entanglement entropy, you can argue that if you have quantum corrections in the bulk, then this SCFT is the sum of this classical piece and a quantum piece coming from the bulk, where this is again this measure S that I defined, but now for quantum fields living in the chambers. So for example, what I mean is here you have this ABCD, and this also naturally gives you a subdivision of the bulk A, B, C, D, with these as the boundaries between them. And if you compute the measure, the 4-partite measure for these guys, this S, then this is what appears on this side. Okay. And now with this, you can try to now use the saturation of the inequalities to characterize the holographic encoding map. In the case of bipartite entanglement, when you do that, when you try to characterize the holographic encoding map using this type of formula, you end up with the bulk reconstruction statement, entanglement wedge reconstruction statement. And I suspect that if one understands this for multipartite case, you might get more understanding, a more detailed understanding of this map. Okay, so at this point I will end. Thank you. We're sorry for going over that.
No, it's very nice. Thanks for the very beautiful seminar. So we should take questions. So let's have questions. Okay, so maybe I can ask. So I think that this is quite impressive, but usually I think in quantum information community, there's especially have to look at measures in which they are monotonic under CPTP. So your statement is that these measures have this, you have proof that this actually is monotonic under CPTP map?
Yes, we do have a proof. It is a slightly different story. So let me just, so this is something that we are exploring separately. Let me just give you a trailer of what we are doing. So it turns out, as you said, that they are indeed monotonic under CPTP, but there is a more accurate way of saying it, to define what are called entanglement monotones. So you demand that measure, quantity is a good measure of entanglement, not just if it is monotonically decreasing under CPTP map, but if it is monotonically decreasing under CPTP map on average. Okay, these two, so the latter statement is stronger. Okay, and that is convex. So you demand these two conditions. And if you demand these two conditions, then you can obtain an operational, you can make these measures operational. So if you want to, let's say, do the following, you have a state psi distributed across the parties, and you want to do LOCC operations, you want to do something in your lab, and you want to call other people, see what they did, and so on, and you want to take this psi to phi, you can ask, what is the success probability? What is the optimal success probability with which you can do this operation? Okay. Now, using these measures, meaning the quantities which obey this property, that they are monotonic under LOCC on average, not just monotonic under LOCC, but monotonic under LOCC on average, and concave convexity, you can bound these probabilities. This probability can be bounded by the so now in this context, these measures are called entanglement monotones. Let's say mu. So you can bound these probabilities by mu of psi divided by mu of phi. If you compute mu of psi divided by mu of phi, this is a bound on the success probability of this transition. So we are in this context writing down some entanglement monotones. So the measure S that I talked about, well, not quite S, but something related to E. You cannot take log. It turns out you cannot take log. but you have to do like 1 minus e to some power, 1 minus e to the power 1 by 2 to the power q minus 1 or something like that. And then this starts enjoying the properties that I mentioned. Namely, it is monotonic under LOCC on average. So it's a stronger condition than just monotonicity under LOCC, as I said. And then using this, you can start bounding the transition probabilities. So this kind of thing, direction that we are exploring purely from quantum information theory point of view. And unfortunately, I have not yet seen any application of this in holography. Maybe in some teleportation, this Gauge-Ferris-Wall teleportation, etc. This could be useful, but I don't know. But yeah, I agree that this is a nice direction to explore there.
Well, I mean, it could be probably interesting generally to understand the RG flow characterization of how these things happens and whether
Abhijit, for q equal to 4, that measure that you kind of constructed, is it somehow related to the Cayley's hyperdeterminant?
Good question. Yeah,
because it looks like, means in 2010, around that time, there was this black hole qubit correspondence, and some people wrote, and yeah, it very much looked like, although I am not sure, but yeah, very much looked like for q equal to 4, when instead of Fs you make a cube, and somehow there might be some relation. Do you know of something?
Yeah, there may be some relation, but one thing that makes me say no is the following. So I guess when you say this hyperdeterminant, that's defined only for qubits, right? 4 qubits.
Right.
Yes. Usually these determinant kind of objects, they are invariant not just under local unitaries, but invariant under local special linear transformations. Because that's why determinant is kind of more of an invariant than just traces, right? Because it is invariant under special linear transformation also. And these things that we constructed, they're certainly not invariant under local linear transformation. But maybe for qubits specifically, it may end up being the same, but I suspect that it's not, even for qubits.
Okay, thank you.
Good. Let's see if there are further questions.
I have a question which is probably pedagogical, I suppose.
Yeah, please.
Hello. So, I mean, when you say orbifolds and conical singularities, so I mean, if I take a piece of paper and I fold it in half, right?
Yes.
So that creates I guess a line singularity, you could call it, right?
No, it does not. You have to put peanuts in it and eat, then it will become cone.
You have to put what? Sorry?
You have to make a cone, right? I mean, the one that you get when you put peanuts in. That's the conical singularity. Just by folding.
Right. That's what I'm saying. That's what I'm saying is that if you fold it once, you get like a line singularity, and then if you fold it twice,
call it a singularity. Okay, it's not a conical singularity. It's
no. Okay, fine. And then if you fold it twice, then you get that's a conical singularity, right? And that's an orbifold, right? I mean, in a very simple manner of speaking.
Okay. Fine. I mean, better way to think about it is that you cut out a pizza slice and then glue it like this.
Right.
Yeah, okay. That's the conical singularity, and the angle that you cut out is the deficit angle.
Right. No, that I understand, but just trying to understand in the context of the ADS spaces here, and the relation of the singularity structure to the graphs associated with the boundary state.
Okay, I thought the question. Anyway, I did not get the question. Then what is the question? You were talking about paper and folding the paper, so I don't quite understand how this question is related to that.
I'm really sorry. Actually, I have to.
Okay, sure.
End it because I have a cutoff actually. Yeah, I think
we can talk offline also. If you're
offline, yeah, maybe you can continue. So let me thank Abhijit again for this great seminar, and let me stop the recording also.
Thank you, Ayan. Thanks again.